What if the brightest stars in our sky are the ones that could erase us? The voice cuts through silence like a blade through velvet, measured, contemplative, carrying the weight of terrible knowledge. Below, Earth spins in its ancient dance, a sphere of impossible blue wrapped in whispers of white cloud, bathed in the gentle kiss of starlight. A billion distant suns paint silver streams across continents and oceans, their photons completing journeys that began before human civilization existed. From up here in the void between worlds, in this pressurized can of aluminum and hope we call a space station, everything looks eternal, peaceful, safe. But appearances, as any astronomer will tell you, are the universe's greatest deception. My name doesn't matter. Call me an observer, a watcher, someone who has learned to read the universe's hidden language written in spectral lines and radiation signatures. I've spent 37 years tracing photons across the cosmos, decoding messages written in wavelengths humanity barely understands, translating the whispers of dying stars into warnings we're almost too primitive to comprehend. What I've discovered in those decades of vigil keeps me awake in the artificial night of this orbital station, staring at screens that show me beauty and terror in equal measure. You see that gorgeous tapestry of light surrounding our pale blue dot, that celestial artwork that has inspired poets and lovers for millennia, that has guided sailors across dark oceans and travelers across endless deserts. It's also a minefield. Each brilliant point contains the potential for annihilation, stellar furnaces burning through their fuel supplies, some steadily, some erratically, all eventually destined for spectacular death. And the most beautiful ones, the giants that burn brightest in our winter sky, those azure and crimson jewels that children learn to identify before they can properly write their own names, those are the ones we should fear most. I float here 370 kilometers above the Earth's surface in a module specifically designed for long-duration stellar observation. The walls around me hum with the electricity of a dozen monitoring systems, each one trained on a different cosmic threat. My colleagues below think I'm paranoid, dedicating my life to watching stars that probably won't explode for thousands of years. But they don't understand what I understand. They haven't run the simulations 10,000 times, haven't traced the light paths of potential gamma-ray bursts across their projection of Earth's future position, haven't calculated the odds down to the 15th decimal place. The universe isn't malicious. It's something far worse. It's indifferent. And in that indifference lies a truth more terrifying than any conscious threat. We exist at the mercy of cosmic forces that don't even know we're here. Tonight, as every night for the past 3 years since I took this assignment, I watch the Watchers, 3 stellar monsters that dominate not just my screens, but my nightmares. Each one is a ticking bomb with a fuse measured in astronomical time, which sounds comfortingly long until you realize that in cosmic terms, the difference between tomorrow and 1,000,000 years from now is less than a rounding error. The station's life support systems cycle with mechanical precision, pumping recycled air through filters that smell perpetually of industrial plastic and human anxiety. Outside my observation window, the cosmos wheels in its ancient patterns, constellations rising and setting as Earth turns below. It's been 4 hours since my last break, but I can't leave my post, not yet, because tonight, like every night, might be the night one of them finally lets go. 3 cosmic titans dominate my screens tonight, their data streams painting portraits of impending catastrophe in false color imagery and spectroscopic analysis. Each monitor tells a different story of stellar death, written in wavelengths invisible to human eyes, but translated by our instruments into charts and graphs that spell doom in mathematical precision. First, there's the red giant everyone knows, that rusty jewel marking Orion's shoulder. Betelgeuse. Even the name carries weight, derived from ancient Arabic, meaning the giant's shoulder or perhaps the armpit of Orion, depending on which etymologist you believe. At 640 light-years distant, this stellar colossus pulses with the irregular heartbeat of a dying god. When I say dying, I mean it in the most literal sense. This star is in its final evolutionary stage, a red supergiant that has exhausted the hydrogen in its core and now burns heavier elements in shells like a cosmic onion, each layer fusing different atoms in a desperate attempt to stave off gravitational collapse. The numbers are staggering. Its diameter, if you placed Betelgeuse where our Sun sits, its surface would engulf the orbits of Mercury, Venus, Earth, Mars, and nearly reach Jupiter. That's a sphere of superheated plasma over 700 times wider than our life-giving star, pulsing and convecting with cells of hot gas each larger than the distance from Earth to the Moon. Its surface roils with convection patterns that dwarf our entire solar system, rising plumes of million-degree plasma that would appear as continents of fire if we could see them clearly. But here's what keeps me staring at its data. Betelgeuse has been acting strange. In late 2019 and early 2020, it dimmed dramatically, dropping to about 40% of its usual brightness. The astronomical community buzzed with speculation. Was this it? Was this the beginning of the end? Turned out it was just a massive ejection of material that cooled into dust, obscuring our view. But that event taught us something crucial. Betelgeuse is unstable in ways we're only beginning to understand. My instruments track its every fluctuation. Tonight, its infrared signature shows normal variability, the star breathing in and out on a roughly 400-day cycle, with smaller oscillations overlaid like harmonics on a fundamental frequency. The computers calculate its remaining lifetime in geological blinks, maybe tomorrow, maybe 100,000 years from now. In cosmic terms, that's the difference between inhaling and exhaling. When you're talking about a star that's existed for 8 million years, 100,000 years is nothing. It's 1.25% of its lifetime, the stellar equivalent of the last few minutes of a human life. 7,500 light-years away, in the constellation Carina, lurks something even more violent. Eta Carinae isn't just a star, it's a binary system of hypergiant stars locked in a death spiral that defies comprehension. The primary star weighs in at around 100 to 120 solar masses, while its companion, which would be considered massive by any other standard, contains merely 30 to 80 times our Sun's mass. Together, they outshine our Sun 5 million times over, pouring out radiation at rates that would strip a planet's atmosphere in days if it were too close. The system fascinates and terrifies in equal measure. Every 5.5 years, the two stars sweep close to each other in their elliptical orbits, passing at a distance comparable to the space between Mars and the Sun. During these encounters, their stellar winds, streams of charged particles racing away at velocities exceeding 1,000 kilometers per second, collide with such violence that they generate X-rays visible from Earth despite the vast distance. The collision zone reaches temperatures of 100 million degrees, hot enough to forge heavy elements in the chaos of stellar wind interaction. But Eta Carinae's most spectacular feature is its history of violence. In 1843, it underwent what astronomers call the Great Eruption, suddenly becoming the second brightest star in Earth's sky despite being 7,500 light-years away. Over the course of 20 years, it ejected more than 10 solar masses of material. Imagine 10 entire stars worth of gas and dust blown into space at hundreds of kilometers per second. That material now forms the distinctive homunculus nebula, a bipolar structure that looks like a cosmic peanut in our telescopes, glowing with the reflected light of the monsters at its heart. The eruption itself remains a mystery. Current theories suggest it might have been a failed supernova. The star almost died but somehow recovered, though recovered is a relative term for something so fundamentally unstable. My instruments detect smaller eruptions happening regularly, mass ejections that would be catastrophic events for any other star, but barely register as hiccups for this monster. Each night, I measure the Doppler shifts in its spectrum, track the temperature fluctuations in its photosphere, count the X-ray photons streaming from its wind collision zone. Each measurement is another data point in humanity's death watch. But the one that truly haunts my calculations sits 8,000 light-years away in Sagittarius, WR 104, a Wolf-Rayet star, one of the rarest and most extreme objects in our galaxy. Wolf-Rayet stars are the exposed cores of massive stars that have blown away their outer layers through stellar winds so powerful they make solar wind look like a gentle breeze. WR104 loses mass at a rate of 1 Earth mass every year. Imagine our entire planet, everything you've ever known and loved, converted to stellar wind and blown into space annually. What makes WR104 special, and especially terrifying, is its geometry. It's part of a binary system, spinning with its companion star once every 241 days. This rotation, combined with its massive stellar wind, creates a pinwheel pattern of dust that we can actually observe from Earth. The spiral structure acts like a cosmic lawn sprinkler if lawn sprinklers sprayed million-degree plasma and hard radiation instead of water. But here's the terrifying part. The system's rotation axis might point directly at our solar system. The uncertainty in that word, might, keeps me up at night. We can't measure the exact orientation with our current instruments. There's a cone of uncertainty, maybe 16 degrees wide, and Earth sits somewhere within that cone. If we're directly in line with WR104's poles, when it finally explodes, and it will explode, probably within the next few 100,000 years, it won't just be a supernova, it will be something far worse, a gamma-ray burst. I pull up the latest spectroscopic data on WR104. Its spectrum is a forest of emission lines, ionized helium, carbon, oxygen, all the signatures of a star that has burned through its hydrogen, burned through its helium, and is now fusing heavier elements in a desperate race against gravitational collapse. The carbon lines are particularly strong tonight, glowing with an intensity that speaks to temperatures exceeding 50,000 Kelvin at the star's surface, nearly 10 times hotter than our Sun. Let me explain what happens when titans fall, when stellar monsters like these finally lose their billion-year battle against gravity. It's a process so violent, so fundamentally extreme, that human language lacks proper words to convey the scale of destruction. When a massive star exhausts its nuclear fuel, the chain of events that follows happens with breathtaking speed. For millions of years, the star maintains a delicate balance, the outward pressure of nuclear fusion fighting against the inward pull of gravity. It's a cosmic tug-of-war where both sides are perfectly matched, but nuclear fuel doesn't last forever. Eventually, the star runs out of elements to fuse in its core. When that happens, when the fusion reactions finally cease, gravity wins instantly and catastrophically. The collapse happens in less than a second. One moment, you have a core of iron, the ash of all previous fusion reactions, iron being the element where fusion no longer releases energy, sitting at the star's heart. The next moment, that iron core, which might be the size of Earth but contain the mass of our Sun, collapses. The matter crushes inward at speeds approaching 70,000 kilometers per second, nearly a quarter the speed of light. Electrons are driven into protons, forming neutrons and releasing a flood of neutrinos. The density becomes so extreme that a teaspoon of this matter would weigh as much as Mount Everest. Then comes the rebound. The collapsing matter hits a point where it literally cannot compress any further. The strong nuclear force finally pushes back against gravity. The infalling material bounces off this incompressibly dense core like a tsunami wave hitting a seawall. The rebound shockwave races outward through the star's layers, heating them to billions of degrees, triggering fusion reactions that in seconds forge more heavy elements than the star created in its entire lifetime. A single supernova releases more energy in the first 10 seconds than our Sun will produce in its entire 10 billion year lifetime. The explosion shines with the light of 5 billion suns, briefly outshining an entire galaxy. If Betelgeuse were to explode tonight, it would appear in our sky as bright as the full moon, visible even in daylight, casting shadows at night. For weeks, it would be the most brilliant object in Earth's sky after the Sun, a cosmic lighthouse marking the death of a giant. But light, visible light that we can see with our eyes, is just a tiny fraction of a supernova's output. The real energy emerges across the entire electromagnetic spectrum, radio waves that would overload every receiver on Earth, infrared radiation that would be detected by satellites designed to spot forest fires, ultraviolet rays that would trigger aurora displays at latitudes where they've never been seen, X-rays that would penetrate Earth's magnetosphere, and those invisible killers, gamma rays. Gamma rays are photons, particles of light, but calling them light feels like calling a nuclear weapon a firecracker. These are photons with energies millions of times greater than visible light, wavelengths so short they're smaller than atoms. When a gamma ray hits matter, it doesn't just warm it like infrared or tan it like ultraviolet. It tears apart molecular bonds, ionizes atoms, shatters DNA. A single gamma-ray photon carries enough energy to destroy thousands of chemical bonds in living tissue. Now imagine not just one gamma-ray, but a focused beam of them. That's what a gamma-ray burst is, nature's ultimate death ray. When certain massive stars collapse, the physics of the explosion channels a significant fraction of the energy into two jets emanating from the star's poles. These jets punch through the collapsing star and emerge into space as searchlights of destruction, each carrying as much energy as our sun will produce in its entire lifetime, focused into a beam narrower than the full moon as seen from Earth. The jets travel at 99.995% the speed of light, so close to light speed that relativistic effects come into play. From our perspective, the jet appears compressed, its energy blue-shifted to even higher frequencies. What starts as merely X-rays in the jet becomes hard gamma radiation by the time it reaches us. The beam is so tightly focused that it could travel across the entire galaxy and still maintain enough coherence to cause damage. I've run the simulations 1,000 times, maybe more. Each time, I adjust the parameters slightly. The distance to the star, the energy of the burst, the angle of the beam, the density of intervening interstellar material. The results vary in their specifics, but never in their general conclusion. If Earth is hit by a gamma-ray burst from within 10,000 light-years, the consequences range from catastrophic to existential. The nearest scenario, the one that keeps me staring at WR104's data, goes like this. The star collapses. The jets form and stabilize within seconds. One of them, through cosmic coincidence or cruel fate, points directly at our solar system. The gamma rays race toward us at the speed of light. No warning, no precursor, no chance to prepare. 8,000 years after the star dies, on what starts as an ordinary day on Earth, the wavefront arrives. The first systems to detect it would be our gamma-ray satellites, swift, Fermi, integral if it's still operational. They would register a spike in gamma radiation unlike anything in their operational history. Automatic alerts would be sent to ground stations, but by then it would already be too late. The gamma rays would already be hitting Earth's atmosphere, and the cascade of destruction would have begun. Earth has defenders, though calling them shields gives far too much comfort. They're more like tissue paper barriers against cosmic blowtorches, lucky accidents of geology and magnetism that have allowed life to persist in this hostile universe. Our first line of defense is the magnetosphere, that invisible bubble generated by our planet's molten iron core spinning within the mantle. This dynamo effect creates a magnetic field that extends tens of thousands of kilometers into space, an invisible force field that deflects the solar wind and low-energy cosmic rays. We see its work in the aurora, those dancing curtains of green and red light at the poles where charged particles, funneled along magnetic field lines, collide with atmospheric gases and cause them to glow. The magnetosphere is remarkable in its complexity. It's not a simple bubble, but a dynamic, ever-changing structure that responds to the solar wind, like a flag responds to earthly wind. On the sun-facing side, it's compressed to within 10 Earth radii of our planet. On the night side, it streams out like a comet's tail for hundreds of thousands of kilometers. During solar storms, it rings like a bell, oscillating with frequencies we can detect as changes in compass readings and fluctuations in power grids. But against a nearby supernova's assault, against the focused fury of a gamma-ray burst, our magnetic shield is tissue paper before a blowtorch. Gamma rays don't care about magnetic fields. They're electrically neutral photons that pass through magnetic fields as if they don't exist. The magnetosphere that protects us from solar storms would offer exactly zero protection against the kind of stellar assault we're discussing. Above us, starting at about 15 kilometers altitude and extending to 35 kilometers, floats the ozone layer. It's absurdly thin. If you compressed all the ozone in the atmosphere to sea level pressure, it would form a layer only 3 millimeters thick. 3 millimeters of gas, spread across the entire planet, is all that stands between us and the sun's ultraviolet radiation. This fragile veil exists in a constant state of chemical equilibrium. Oxygen molecules, O2, in the upper atmosphere are split by ultraviolet light into individual oxygen atoms, which then combine with other oxygen molecules to form ozone, O3. The ozone absorbs ultraviolet light, splits back into O2 and O, and the cycle continues. It's a beautiful system, elegant in its simplicity, effective in its function. Life as we know it exists because this thin chemical veil blocks the sun's harsher wavelengths. Without it, UV radiation would reach Earth's surface with enough intensity to cause severe burns in minutes, trigger epidemic rates of cancer, and damage the DNA of every living thing exposed to daylight. The plant life that forms the base of our food chain would wither and die. The phytoplankton in the oceans, which produce more than half of Earth's oxygen, would be decimated. One good gamma ray burst could strip away half of our ozone layer in seconds. The chemistry is brutally simple. High-energy photons shatter nitrogen molecules, N2, in the atmosphere into individual nitrogen atoms. These atoms then react with oxygen to form nitrogen oxides, NO and NO2. These compounds are catalytic ozone destroyers. A single molecule of nitrogen oxide can destroy tens of thousands of ozone molecules before it finally rains out of the atmosphere. But the destruction doesn't stop there. The nitrogen oxides would form a brown smog in the upper atmosphere, absorbing sunlight and creating what scientists call a cosmic winter. Temperatures would plummet as less sunlight reaches the surface. The brown haze would be visible from the ground. The blue sky we take for granted would turn a sickly brown orange, like the air over the most polluted cities but covering the entire planet. The atmosphere itself, all 5.15 times 10 to the 18th kilograms of nitrogen, oxygen, argon, and trace gases we breathe, would become a weapon turned against us. Under intense stellar radiation, the air would ionize. Nitrogen and oxygen molecules would be stripped of their electrons, creating a plasma, the fourth state of matter. The air itself would glow with an eerie light, like being inside a planet-sized neon sign. The ionization would create massive electrical imbalances, triggering lightning storms of unprecedented intensity. Every thunderstorm on Earth today would pale in comparison to the electrical chaos of an atmosphere trying to re-establish electrical neutrality after a gamma-ray assault. The heating would be immediate and extreme. As gamma rays and X-rays are absorbed by the atmosphere, their energy has to go somewhere. It goes into heat, tremendous, sudden heating of the upper atmosphere. The heated air would expand, potentially blowing away a significant fraction of our atmosphere into space, especially the lighter gases like hydrogen and helium, but potentially even heavier molecules if the heating is severe enough. I watch the data streams from atmospheric monitoring stations scattered across the globe. Mauna Loa, the South Pole, balloon-borne sensors that ride the jet stream. They track ozone concentrations down to parts per billion, measure the isotopic composition of atmospheric gases, monitor the flux of cosmic rays that manage to penetrate our defenses. Everything reads normal tonight. Ozone at 320 Dobson units, well within the healthy range. Cosmic ray flux at typical levels for this point in the solar cycle, the magnetosphere humming along at its usual frequency, everything fragile, everything temporary. We're children playing in a cosmic shooting gallery, protected by nothing more than luck, distance, and the random orientation of stellar rotation axes. The most insidious part is how quickly it would happen, not the stellar collapse itself. That's instantaneous on human timescales, but the unraveling of our protections, the cascade of atmospheric chemistry that would follow a gamma-ray burst that would take just days to weeks. We could watch our shields failing in real time, helpless to stop it. Satellite instruments would track the ozone depletion spreading from the point of impact, probably one of the poles if the burst came from outside the ecliptic plane, like watching a time-lapse video of fruit rotting. Within days, UV levels at Earth's surface would rise to lethal levels. Weather patterns would shift as the atmospheric heating changed circulation patterns. The jet streams that govern our climate would be disrupted. Hurricanes would form in places they've never been seen. Droughts and floods would ravage agricultural regions. And all the while, that brown haze would thicken, blocking more and more sunlight, cooling the planet even as UV radiation scorched any life exposed to daylight. Here's what keeps me staring at these screens through the endless night, what makes me check and recheck the spectroscopic data with obsessive precision. One of them might already be dead. Light has a speed limit, 299,792,458 meters per second in vacuum, a cosmic speed limit that nothing with mass can ever reach and nothing without mass can ever exceed. It seems fast to us. Light can circle Earth's equator 7.5 times in a single second. It can travel from Earth to the Moon in 1.3 seconds. But on cosmic scales, light is frustratingly, terrifyingly slow. When I observe that red supergiant Betelgeuse through our instruments, I'm not seeing it as it is. I'm seeing it as it was 640 years ago, around the year 1385, when we account for current date. That's when Geoffrey Chaucer was writing the Canterbury Tales, when the Ming dynasty had just risen to power in China, when the Black Death's aftermath was still reshaping European society. The photons hitting our detectors tonight began their journey when medieval knights still rode into battle and the printing press hadn't yet been invented. The light from Eta Carinae is even older. 7,500 years of travel time means we're seeing it as it was around 5,500 BCE. That's before the first Egyptian dynasty, before writing was invented in Mesopotamia, when humans were just beginning to develop agriculture along the fertile river valleys. The great eruption we observed in 1843, that actually happened around 5,657 BCE. We're always playing cosmic catch-up, always behind the universal curve. And WR104? That photon stream began its journey 8,000 years ago, around 6,000 BCE. That's the late Neolithic period, when humans were just beginning to work with copper, when the Sahara was still green and fertile, when the English Channel was forming as rising seas finally separated Britain from continental Europe. Everything we know about this star, every measurement and observation, is 8 millennia out of date. This temporal disconnect creates a special kind of existential dread. Right now, at this very moment, any one of these stellar bombs might have already detonated. The collapse could have happened centuries or millennia ago, and we wouldn't know. Couldn't know. The information simply hasn't reached us yet, crawling across the light years at the maximum speed the universe allows. Imagine it. Betelgeuse might have collapsed in the year 1650, during the height of the scientific revolution. Galileo's discoveries about the moons of Jupiter would have been fresh in academic memory. Newton would have been a child, and somewhere in Orion, one of the night sky's most prominent stars would have been undergoing the most violent process in nature. The neutrinos from that collapse, ghostly particles that barely interact with matter, would have passed through Earth in 2290, completely undetected because we hadn't invented neutrino detectors yet. And the light, the visible announcement of Betelgeuse's death, it would still be 265 years away from reaching us. Or consider an even more unsettling scenario. WR104 might have exploded 7,999 years ago, just 1 year after the light we're seeing now began its journey. That means the death light has been racing toward us for nearly 8,000 years, crossing the void between stars, inevitable as mathematics, unstoppable as time itself. Every human civilization, Sumer, Egypt, Greece, Rome, the rise and fall of empires, the entire span of recorded history, all of it would have existed in the shadow of an approaching catastrophe that no one could see coming. We could be living in the last peaceful decades or centuries of human civilization, blissfully unaware that our fate was sealed before the pyramids were built, before humans invented the wheel, before we painted those caves in Lascaux. The most terrifying part? If WR-104 has already collapsed, if its poles are indeed aimed at us, and we're still not certain about that alignment, that crucial angle that makes the difference between light show and extinction, the gamma rays are coming. They're not might be coming or could be coming. They are coming right now, crossing interstellar space at the speed of light, and there's absolutely nothing we can do to stop them. No warning, no time to prepare, no last-minute scientific breakthrough that could save us. Just one day, a day that might be tomorrow, or might be in 1,000 years, the satellites will scream their electronic death cries as their circuits are fried by radiation levels they were never designed to withstand. The International Space Station's radiation alarms will trigger simultaneously. Astronauts will have minutes, maybe less, to reach whatever shielding they can find. Though against a full gamma-ray burst, even the station's most protected areas would offer little safety. On Earth, the effects would begin immediately. Radio communications would fail as the ionosphere, that layer of charged particles that allows radio waves to bounce around the planet, is thrown into chaos. GPS satellites would malfunction or die entirely, their delicate electronics overwhelmed by induced currents. The power grids, those vast networks of transmission lines that act like continental-scale antennas, would experience induced currents that could blow transformers from Canada to Mexico simultaneously. And then the ozone depletion would begin. Not the slow, gradual depletion we worried about from chlorofluorocarbons in the 1980s, but a sudden, catastrophic loss. Within days, the ozone layer would be torn apart, its careful chemical balance destroyed by the cascade of nitrogen oxides created by the gamma radiation. UV levels would spike to levels not seen on Earth since before the oxygenation event 2.4 billion years ago. By the time we see their death, their light has already reached us. That's the cruel irony of stellar observation. The moment we detect a supernova, the moment we see that sudden brightening that tells us a star has died, it's already over. The explosion happened years, decades, centuries, or millennia ago. We're not watching stars die. We're watching recordings of deaths that have already occurred, cosmic snuff films played out at the speed of light. I pull up the latest data on all three monsters, cross-referencing observations from multiple observatories. Betelgeuse's spectrum shows the usual absorption lines, the chemical fingerprints of elements in its outer layers. Hydrogen, helium, carbon, nitrogen, oxygen, all present in the expected ratios. But are those ratios from 640 years ago telling us about a star that still exists? Or are we looking at the spectrum of a ghost? Eta Carinae's periodic brightening continues on schedule, the 5.5-year dance of its binary components as predictable as clockwork. But that clockwork is 7,500 years old. For all we know, one of those close passages finally triggered the instability that pushed the system over the edge. The collision of stellar winds might have disrupted the primary star's core, initiated a collapse that even now, sends death light streaming across the cosmos toward our small, fragile world. WR-104's pinwheel continues to turn in our images, that elegant spiral of dust and stellar wind that makes it one of the most photogenic objects in our galaxy. Every 241 days, it completes another rotation, spraying its stellar wind in our general direction like a cosmic lawn sprinkler. But those images are 8,000 years old. That's 12,000 rotations ago. A lot can happen in 12,000 stellar rotations, but humanity doesn't surrender to the dark. We never have. From the moment our ancestors first looked up at the night sky and wondered what those points of light were, we've been watchers, questioners, seekers of truth even when that truth terrifies us. New eyes open across Earth and beyond, each one a technological marvel designed to peer deeper into space and time, to catch the whispers of dying stars before they become screams. The James Webb Space Telescope, launched on Christmas Day 2021, now sits at the second Lagrange point, 1.5 million kilometers from Earth. Its 6.5-meter mirror, made of gold-plated beryllium segments that unfold like an origami flower, peers into the infrared spectrum where dust cannot hide stellar secrets. It watches Betelgeuse with unprecedented resolution, tracking convection cells on its surface, measuring the velocity of ejected material, looking for the telltale signs that collapse is imminent. JWST's instruments can detect the faintest whispers of stellar instability. The NIR spec, near-infrared spectrograph, can simultaneously observe 100 objects, breaking their light into component wavelengths with such precision that we can detect velocity changes of just a few meters per second in stellar atmospheres, thousands of light years away. When Betelgeuse eventually begins its final collapse, the outer layers will start falling inward days or weeks before the explosion. JWST might, just might, catch that infill signature, giving us the only warning we're likely to get. The Fermi Gamma Ray Space Telescope orbits 550 kilometers above Earth, spinning slowly to survey the entire sky every 3 hours. It's our sentinel against gamma-ray bursts, detecting about one per day from distant galaxies, each one a reminder of what these events can do. Fermi's Large Area Telescope can spot gamma rays with energies from 20 megaelectron volts to 300 gigaelectron volts. That's millions to billions of times more energetic than visible light. When a gamma-ray burst occurs anywhere in the observable universe, Fermi knows within seconds. The data from Fermi has taught us disturbing truths about gamma-ray bursts. They're more common than we thought, about one per day that we can detect, which means many more we can't see because they're pointed away from us. They're more powerful than we imagined. Some release as much energy in a few seconds as the sun will produce in its entire lifetime, and they're more focused than we feared. The jets can maintain coherence across billions of light years, arriving at Earth as tight beams of destruction rather than diffuse waves of radiation. Deep beneath the Antarctic ice, where the frozen continent reaches thicknesses of nearly 3 kilometers, sits one of humanity's most unusual telescopes. IceCube doesn't look up, it looks down, using the entire Earth as a filter. It's a cubic kilometer of ice instrumented with 5,160 optical sensors, each one waiting to catch the faint blue glow of Cherenkov radiation produced when neutrinos, those ghostly particles that barely interact with matter, occasionally collide with atoms in the ice. IceCube is our early warning system, our only chance at getting advance notice of a nearby supernova. When a star collapses, 99% of the energy is released as neutrinos, not light. These neutrinos stream out from the dying star at nearly the speed of light, passing through the outer layers of the star as if they weren't there. They reach us hours or even days before the visible light, which has to fight its way out through the exploding stellar material. In 1987, we detected neutrinos from Supernova 1987A in the Large Magellanic Cloud, just 24 neutrinos from an explosion 168,000 light-years away. But that detection, crude as it was with the instruments of the time, proved the principle. If Betelgeuse explodes, IceCube would detect not dozens, but millions of neutrinos. The detector would light up like a Christmas tree, every sensor firing simultaneously as the neutrino wave passed through Earth. We'd have hours, maybe a day, before the visible light arrived, hours to point every telescope on Earth at Orion, hours to alert the world that one of the night sky's most famous stars was about to disappear forever. I'm part of this network now, one voice in a chorus of watchers, all of us searching for signs, for patterns, for hope. The Stellar Observation and Threat Assessment Station, SOTAS as we call it with typical government acronym efficiency, coordinates observations from ground and space-based instruments worldwide. Every night, I compile reports that read like medical charts for dying giants. Betelgeuse showing increased variability in infrared bands 3 through 7. Period analysis suggests multiple overlapping oscillation modes. Recommend increased monitoring frequency. Eta Carinae eruption cycle accelerating. Current period 5.539 years, decreased from 5.541 years last cycle. Wind collision zone showing increased X-ray luminosity. WR 104 rotation period stable at 241.5 days. dust production rate increased by 3% over baseline. Spectroscopic analysis shows enhanced carbon lines suggesting accelerated nuclear processing. We've built early warning systems that could give us hours, maybe days if we're extraordinarily lucky. Not enough time to stop what's coming. You can't stop a supernova any more than you can stop an earthquake or a hurricane, but perhaps enough time to seek shelter, to preserve something of what we've built, to ensure that if the worst happens, something of humanity survives to rebuild. The protocols are already in place, developed by committees of scientists who spent years contemplating the unthinkable. If we detect an imminent supernova within 1,000 light-years or signs of an incoming gamma-ray burst, the alert system triggers automatically. Priority notifications go to world governments, space agencies, and major observatories. Emergency broadcasts would interrupt regular programming worldwide, though what exactly we'd tell 7 billion people about their potentially imminent doom remains a matter of fierce debate in the scientific community. Some argue for full transparency, tell everyone everything, let humanity face its potential end with eyes wide open. Others advocate for careful information management, releasing details gradually to prevent panic. Still others suggest saying nothing until we're absolutely certain, though by then it might be too late for any meaningful response. We've run psychological simulations, sociological models, even brought in philosophers and ethicists to debate the moral implications. How do you tell a planet it might be about to die? The infrastructure we've built goes beyond just detection. Deep beneath mountains in Colorado, Switzerland, and China, governments have constructed reinforced shelters designed to preserve genetic samples, seed banks, and digital archives of human knowledge. They call them continuity vaults, a clinical name for humanity's last-ditch attempt at immortality. If the surface becomes uninhabitable, if UV radiation makes daylight deadly, these vaults might preserve enough to restart civilization once the worst has passed. Space agencies have accelerated their plans for off-world colonies. Mars, despite its thin atmosphere and weak magnetic field, would actually be better protected from a gamma-ray burst than Earth. The angle would be different, the intensity reduced by distance and geometry. The Moon's underground lava tubes could shelter a small population for decades if properly equipped. Even the moons of Jupiter, despite their own radiation hazards from Jupiter's magnetosphere, might offer refuge from a stellar catastrophe. Private companies have joined the effort. SpaceX, Blue Origin, and newer ventures from China and India are developing rapid deployment habitat modules, life support systems that could theoretically keep thousands alive in sealed environments. It's not enough. Could never be enough to save everyone, but it's something. A seed of continuation, a hedge against extinction. Every night, I compile reports, update trajectories, refine calculations. My voice joins transmissions, beaming to observatories worldwide. The Very Large Array in New Mexico listens to Betelgeuse in radio wavelengths, tracking the motion of its outer layers. The Atacama Large Millimeter Array in Chile peers through cosmic dust to observe Eta Carinae's binary dance. Observatories in Hawaii, the Canary Islands, and Australia maintain continuous watch, a global network ensuring that no matter where Earth turns, someone is always watching the watchers. We share everything: data, analyses, concerns, even our fears. The international cooperation is unprecedented. Political rivals, economic competitors, nations that barely speak to each other diplomatically, all share their stellar observations freely, because this threat recognizes no borders, respects no sovereignty, cares nothing for our human divisions. Tonight, I'm analyzing a particularly interesting dataset from Betelgeuse. The star's radial velocity, its motion toward or away from us, shows subtle variations that weren't there 6 months ago. It could be nothing, just another convection cell rising to the surface, material the size of our entire inner solar system bubbling up from the stellar depths. Or it could be the beginning of something more dramatic, the star's outer layers starting their final plunge inward, the last stable breaths before the collapse. I run the data through our prediction algorithms, machine learning systems trained on observations of thousands of other stars, fed with decades of supernova observations. The results are frustratingly ambiguous. Probability of collapse within 1 year, 0.003%. Within 10 years, 0.03%. Within 1,000 years, 3%. The error bars are enormous, our understanding still primitive despite all our technology. We're cartographers of catastrophe, sketching maps of dangers we can barely comprehend. Yet we continue because watching is what humans do. We've always looked up, even when we didn't understand what we were seeing. Cave painters in Lascaux drew the Pleiades on their walls 17,000 years ago. Babylonian astronomers tracked the motion of planets across clay tablets. Chinese astronomers recorded the guest star of 1054, the supernova that created the Crab Nebula. Now we understand too much, see too clearly the dangers that surround us, and still we cannot look away. My shift partner, Dr. Sarah Chen, floats in from the adjacent module, bringing a pouch of what passes for coffee up here. She's been monitoring Eta Carinae while I focus on Betelgeuse, dividing our attention between the monsters. "Any changes?" she asks, though she knows I would have alerted her immediately if there were. "Betelgeuse is breathing heavy tonight," I tell her, pulling up the wavelength analysis on the main screen. "Look at these oscillations in the infrared. The period's shortened by about 3 hours over the last month." She studies the data, her expression thoughtful. Sarah has been doing this longer than I have. 15 years watching stars die, cataloguing their death throes, building predictive models that might one day save our species. "Could be nothing," she says finally. "Remember 2019? Everyone thought that dimming event was the beginning of the end. But what if next time it's not nothing?" I counter. "What if we dismiss real warning signs as just another false alarm?" She doesn't answer immediately. We both know the stakes. Cry wolf too often and people stop listening. Wait too long for certainty and there might not be time to respond. We live balanced on that knife's edge between paranoia and preparedness. "Check this out," Sarah says, transferring her Eta Carinae data to my screen. The wind collision zone has shifted. The X-ray emission is asymmetric now, stronger on the approaching side. Either the secondary star's orbit is evolving, or the primary is losing mass unevenly. I study the false color X-ray images, watching the violent collision of stellar winds heated to millions of degrees. It's beautiful in a terrifying way, like watching two hurricanes collide in slow motion. If hurricanes were made of plasma traveling at thousands of kilometers per second and were larger than our entire solar system. "How's our friend WR104, I ask. Sarah pulls up the latest observations from the Keck Observatory in Hawaii. The infrared images show the distinctive pinwheel pattern, that spiral of dust that makes WR104 so photogenic and so frightening. Stable rotation, consistent dust production. But look at this. She highlights a section of the spectrum. The carbon lines are strengthening. It's burning through its fuel faster than our models predicted. We sit in companionable silence for a moment, two humans in a tin can, watching stars that could kill our entire species, sipping terrible coffee, and somehow making it feel almost normal. It's what humans do. We adapt, we normalize, we find routine even in the extraordinary. "I've been thinking," Sarah says eventually, "about the Fermi paradox." The Fermi paradox, the question of why, in a universe that should be teeming with life, we've never detected any signs of alien civilizations. Scientists have proposed dozens of solutions, from the rare Earth hypothesis to the idea that intelligent life inevitably destroys itself. But sitting here, watching these stellar bombs tick toward detonation, another possibility seems obvious. "Gamma ray bursts," I say, following her thought. "They happen often enough to regularly sterilize large sections of the galaxy. Every few million years, any given solar system might be in the firing line," Sarah continues. "Long enough for life to evolve, maybe even develop intelligence, but not long enough for interstellar civilization to develop. The universe keeps resetting the game board. It's a sobering thought. We might not be alone in the universe, but we might be alone in our time, caught between extinction events, racing against a cosmic clock we can't see.